Sampling theorem. Generally, sampling theorem is used to convert analog signal into digital signal, and different applications are there using sampling. If you go for audio signal, continuous audio signal frequency range is that is approximately 20 Hz to 20 kilohertz. So after conversion from that is physical signal into EM wave, electromagnetic wave. This I am assuming this is the audio signal equivalent. This is the audio signal equivalent. So here, if you convert, this is an continuous signal, that is analog signal. So here, infinite number of times it is defining for each and every second. Here, so at first second, what is an amplitude? At second, what is an amplitude? At third second, what is an amplitude? At fourth second. So like this, can if we go for this analog signal. So here, this is the signal. So continuous signal. So this is converted in the form of digital. Sampling theorem is used to convert analog signal into digital. So here, this is an analog signal and continuous signal. This is the signal. So I am assuming this is an X of t. So here, this is the analog signal. So by using carrier, here you can see this. So this is the carrier signal del of t, and this is the message signal. That is, I am assuming this is an audio equivalent signal, audio signal. So while converting, so this is the carrier sample signal del of t. So here you can see the circuit here. So this is an sample theorem circuit. Here I am giving the audio signal, hello equivalent. So this is an sample signal. You can see this. So after multiplication, after sampling, you will get the sampled output here. So the sample signal, carrier signal is sampled according to the message signal you will call, that is sampling. Here you can see this. This just assume this. This is an sampled output. In real time, that is per a second, 256 samples they can take per a seconds. So means each and every point will be sampled. So of course, after this sample value is converted into digital signal. Final digital encoding techniques. Each and every sample is having that is predefined digital signal, digital equivalent coding. So like this, each point, each and every point, it is predefined. That is predefined digital code is there assigned. If you take any signal, either audio signal or video signal or anything, so after sampling, so they are converted into digital equivalent. By using samples, they are converted into samples. So, but this sampling rate should be having some condition. So that is the sampling rate should be, that is Fs sampling rate should be greater than 2 FM, greater than or equal to 2 FM. Then only we can get the, that is approximate, that is exact signal. After demodulation, you may get the exact analog signal or required signal. If you are not sampled properly, if it is not greater than or equal to 2 FM, so you may not get exact signal. So here, for example, if this is the message signal frequency FM and this is the carrier signal, here you can see this is the carrier signal. I'm assuming this is the carrier signal. So this carrier is varied sample according to the message signal. That is called sampling. But this sample rate should be greater than or equal to 2 fm. For example, here you can see this at least two samples, 2 fm, at least two samples only. So you may get the just assumption this is the first that is 2 fm and this is one more sample. Then only you will get, while demodulating you may get the required original signal. Minimum, that is the sampling rate should be 2. Just assume like this. This is the one sample and this is the one more sample. This sampling rate should be that is greater than or equal to 2 fm. Then only we can get the exact approximate signal. So here you can see this original signal is, this is the original signal, continuous signal, audio signal, and this is the carrier signal. And after multiplier you may get the sampled output like this. This is the sampled signal. Here you can see this. This is the sample signal. Each sample value again it is having predefined coding, digital signal. But the sampling condition is there, that is also called as Nyquist rate, 2 fm. Then only we can recover easily while demodulating the signal. Here you can see this. This is the message signal. This is the message signal. Assume that this is the message signal. And if you want to convert, if you want to go for sampling, so this is the sampling signal or carrier signal. So after sampling you may get like this. This carrier is varied according to the message signal. So this is, of course, there are different samplings are there, that is flat top sampling, natural samplings, different sampling techniques are there. So again it is having that is equivalent to predefined digital equivalent signal, equivalent code. Coming to the application, you can see this in digital communication. Mainly it is used to convert that is analog signal into digital. And even if you go for music and speech, and we can using sampling, you can recording the sampling. And here you can see this even ECG and in medical application MRI machines, samples are continuously transmitting. And even if you go for that is radar signal, the samples are continuously transmitting to detect the required object. And anyhow, that is A to D, DTA, analog to digital or digital to analog converters are required to, that is sampling process. So that is the reason the sampling is required to convert analog to digital and different applications. Thank you. If any doubts or suggestions, you can send to me.